Okay, so now it's time for the talk. So it's my pleasure to introduce Lorenzo Taggi, who is going to talk about macroscopic loops in the interacting Bose gas spin ON and related models. So please go ahead, the floor is yours. Oh, and just a reminder that this talk is being recorded and you can watch it later on our YouTube channel. Okay, thank you very much, Lorenzo.
Okay, thanks for the nice invitation. Welcome everyone to my talk. So in this talk, I'm going to consider a very general random walk loop soup. So I'm going to consider a system of interacting closed random walk trajectories. And the main question for this model is whether a phase transition occurs corresponding to the presence of macroscopic loops as the inverse temperature, so a model parameter is above a certain critical threshold. And this model is related to several other relevant statistical mechanics models. It is indeed a representation of the spin-1 model, which is a very classical important statistical mechanics model which is a spin system. So, and it also includes other models, like, for example, the double dimer model. It is related to the loop 1 model and to the interacting Bose gas. And the structure of my talk is as follows. So I'm going to start from the definition of this very general random walk loop soup. After that, I will discuss some of these connections to the other models. Then I will state a general result about occurrence of macroscopic loops. And if time allows, I will also briefly describe the proof method, which uses a property of the measure, which is referred to as reflection positivity, and also discuss some conjectures, in particular talking about some universal properties of these random loop models in large enough in dimension at least 3. So we'll start then from the definition of this general random walk loop soup. So we consider a graph G, which is an undirected finite graph. And okay, we start with the definition of a loop, more precisely of a rooted oriented loop. What is a rooted oriented loop is a sequence of vertices such that well, the next vertex is a neighbor of the previous vertex, and the last vertex coincides with the first vertex. So essentially, a rooted oriented loop is just a closed random walk trajectory. And in order to be called a loop, we need to have at least 2 steps. Okay, so L is going to denote the set of all rooted oriented loops. Okay, if you have some questions, please interrupt me. And so here we see a representation of a loop. And also here we see the representation of another loop. For example, in this second loop, the sequence goes 2 times to the right and 2 times to the left. And later we define a measure which penalizes the self-intersection. So, for example, the second loop, the second situation will not be so typical. In the typical case, this closed random walk trajectory will really look like a loop. And so cardinality of L is going to denote the number of steps of the sequence. For example, we have a loop of length 2 and a loop of length 6. Okay, and now we are ready to define the model. So this general random walk loop soup is defined as follows. So omega is the configuration space of our model. And each element of omega is an ordered sequence of loops. So each Li is in L. And for example, we see the representation of an element omega. The colors are used to distinguish between different loops. So as you see, each loop okay, gets a label, and in particular, each loop has also a starting point. So it's this a rooted or rooted oriented loop, and so we are going to denote by cardinality of omega the number of loops which are in the element omega. And okay, in order to define the model, I also need to introduce an important quantity, which is referred to as local time. So the local time nx omega counts the number of loops, the number of times the vertex x is being visited by a loop. And it corresponds to the total number of ingoing arrows, which also equals the total number of outgoing arrows that we have at the vertex x in omega. And okay, we are now ready to define the general random walk loop soup. So the definition that I'm going to, the model that I'm going to give depends on a weight function, and which is just a function which assigns to every integer a non-negative real value, and also on some parameters, b, beta, and n. And depending on the choice that we make for the weight function, we obtain some other models of interest. But for the model, for the moment, U is just a general weight function. So just a general function. And the weight which is assigned to the configuration omega is as follows. Now we will discuss all the factors which appear in the definition. Okay, so the weight which is given to the configuration omega, okay, we have a first factor, which is 1 divided by a normalization constant, which makes this P a probability measure. Then we have a factor, which is 1 divided by the number of loops factorial. And so as you can see, okay, from the definition of the model, we have that each loop gets a label. For example, okay, this is an example of a loop configuration, but we can obtain distinct loop configurations just by exchanging the labels. For example, this was now L1 is going to be L2, this was L2 is going to be L3, and this was L3, and this is going to be L1. And how many ways do we have to exchange the labels? This number is number of loops factorial. So the normalization factor that we see here is just a normalization for the number of labelings that you can assign to the loops. Okay, similarly, we have a factor 1 divided by the length of each loop here. Similarly, we can observe that we can, if we take a configuration and now we decide that the starting point of this loop is not this one, but is maybe this one, we obtain a new distinct configuration. And how many choices we have to choose, how many possibilities we have to choose the starting point of such rooted oriented loop, namely the root of the loop. Well, this number is cardinality of L4. So this factor which appears here is just a normalization for the number of possibilities that they have to choose the root, in a sense. Then we have the factor beta to the length of the loop. And so beta is a parameter in the model. And as we increase beta, we typically increase the length of the loop. So we increase the typical length of the loops. And what we want to do is to characterize the occurrence of phase transition with respect to the variation of the parameter beta. Then we have a factor n½ to the number of loops. The role played by this factor will be clarified later. Indeed, n is going to correspond to the number of components of the spins. And so later we will see n appearing natural way from the definition of the spin system. And U is, as I said, is a weight function, and the loops interact, which gives a weight to the local time. And it is the weight function which decides how the loops interact with each other. So according to this definition, we have some local interactions, and the specific type of interaction depends on the choice of the weight function. And we obtain several interesting models as we make a choice for the weight function. Let's start from an example from a possible definition of the weight function, also to fix the definition. So according to this choice of the weight function, for example, so we see that the UN is chosen to be the indicator that the local time is less or equal than m. So if we make this choice of the weight function, then in this random walk loop soup, the loops, so it is not possible to have local time larger than m at any vertex. So in this case, the interaction between the loops is precisely due to the fact that we have an upper bound for the total number of times a vertex can be visited. And this is a challenging case already because this type of weight function introduces hardcore constraints in the system. And also an observation is that, okay, which will be useful for later, is that if we choose this weight function and we consider the model in a finite graph and we consider the limit as beta, which goes to infinity, then we obtain a model in which with probability 1, the local time at each vertex is precisely the maximum value which is allowed by the weight function. So with probability 1, in this case, if we take the limit beta, which is goes to infinity, we get a model where the local time is precisely m at each vertex. And this can be computed easily by one can compute precisely the probability of this event in the limit. Okay, so an important definition for the weight function is the following. So we introduce the range of the weight function. The range of the weight function is the maximum value of the local time which is allowed by the weight function. So for example, in the example that we have seen before, okay, the weight function is the indicator that n is less or equal than m. So the range of this weight function is just m. And well, the models we will consider might have infinite or finite range. For example, for the spin-one model, the weight function will have infinite range. And also, before going ahead, let us also give a sufficient condition for the well-definedness of this measure. So the model is well-defined if the weight function is good. What does it mean? Good means that the bound, the display that, the bound that you see holds. So for there exists an m such that uniformly in n, this inequality holds. And this means essentially that asymptotically, the tail of the weight function is decaying fast enough. For example, if un is 1 divided by n factorial, then this condition is fulfilled, or if the weight function is the way as we defined before, also this condition is fulfilled. Okay, so the question is, do we see a phase transition in this model as we change the value of the parameter m? And for example, more precisely, a phase transition which separates a regime where the loops are all small, as in the following drawing, where we see many small loops, maybe macroscopic connected components of loops, but small loops, from a regime where instead the loops are macroscopic and are of the same size of the volume of the system. And this is the question that we want to answer in this talk. But before coming to the answer, let us discuss the connection to other models. So as I said, there is first connection to spin systems with continuous symmetry, or with the spin-one model, okay, which is a classical spin system where on each vertex, so we have a spin which lives in the unit sphere of dimension n-1. So n is an arbitrary positive integer. And the configuration space is a product space, and it is such that at each vertex we have a spin, okay, which lives in the unit sphere. And the model is defined through the following expectation operator, which is defined as follows. So we have 1 divided by a normalization constant. And then we integrate with respect to a product of Lebesgue measures. And then we have a factor, a Boltzmann factor, which favors the mutual alignment between spins, because beta is going to be non-negative in this talk. And the normalization is such that the average of the function 1 is 1. Okay, this defines the spin-1 model, and we obtain as a special case the easy model, in which case the symmetry is discrete when n is equal to 1, the so-called XY model where n equals 2, and the Heisenberg model where when n equals 3. The model is very interesting for any value of n, and in particular, the analysis, the rigorous analysis becomes more challenging if we increase the value of n, because some important tools which are available for low values of n are not available anymore as n is large. For example, starting from n equal 3, we have no Genebra inequalities. Starting from n equal 4, there is no Lee and Yang theorem. So the analysis becomes more challenging as n is large, and the model is interesting for all values of n. And so let us discuss the connection to the spin system. So I will, so this connection was found by Bridges, Furlich, and Spencer in the 82. And the connection holds if we make a special choice for the weight function, which is, as you see in the display, so it is a weight function which strongly penalizes the local time. So we have strong repulsive interactions. So we have, in particular, 1 divided by an exponential factor which grows exponentially fast times the gamma function, which grows as n factorial. And the connection is as follows. So first of all, the partition functions of the two models are the same. And secondly, the spin-spin correlation function corresponds to a ratio of partition functions, where in the denominator, you see the partition function of the random walk loop soup under the special choice of the weight function. And in the numerator, you see an object which I do not define precisely, which corresponds to somehow a modified partition function with an arbitrary number of loops, precisely as I defined before. But the difference is that one of these loops is open, and it is in particular a loop starting at x and ending at y. So it is a random walk starting at x and ending at y. And the interactions are between these loops, including the open loop, are the same as before, the same as in the definition of the measure. And okay, let us discuss the phase transition in the spin system. So I will only consider the case of dimension at least 3. So we have a famous result from Furlich, Simon, and Spencer, stating that if the graph is the torus in dimension at least 3, n is an arbitrary integer and beta is large, then we have that the spin-spin correlations do not decay to 0 with the distance between the spins, but they stay uniformly positive. And okay, the proof is uses reflection positivity, and the result that we are going to state is essentially a reformulation of this proof technique in a completely different space, which does not use spins, but is implemented in the space of closed random walk trajectories. So the result that I stated is actually stronger than what was proved by Furlich, Simon, and Spencer. Indeed, the uniform positivity in x and y follows from some monotonicity properties which have been proved recently, because the original result states only some uniform positivity of this Cicero sum of spin correlation. And this theorem, which I stated, proves the occurrence of a phase transition from the point of view of the decay of correlations, because when beta is small, it is known that by classical arguments like cluster expansion, that the spin-spin correlation decays exponentially fast with the distance. So coming back to the equivalence, okay, there is a phase transition in the spin model, which is characterized by the fact that we have different behavior of the spin-spin correlation. And this phase transition cannot be directly translated into a phase transition for the random walk loop soup, because this ratio that you see in the right-hand side cannot be interpreted as the probability of some event in the random walk loop soup. And the question for this talk is precisely to characterize then the phase transition also in the random walk loop soup. So I want to understand what happens to the law of the loops. And we want to answer this question more generally. So not only for this weight function, but we want to address this question more generally for without using this connection to the spin system, and without using the relation to without using the result of Fröhlich, Salmon, and Spencer, which works in particular for this weight function. Okay, let us move to other interesting connections. So, this is the case of the model, which is called random lattice permutation. In this case, the weight function is just the indicator that the local time is at most 1. So in this case, the loops are self-avoiding and mutually self-avoiding. And well, combinatorially understanding the behavior of this model is very hard, because the combinatorics already of a single self-avoiding walk is understanding the combinatorics of a single self-avoiding walk is quite hard, and the problem is even harder if we have a system of an arbitrary number of self-avoiding walks. So, okay, we'll not explain why this model is referred to as lattice permutation. There is a connection to the model of random permutations, where each vertex is mapped through the permutation to a nearest neighbor or to the vertex itself. But I will discuss more in particular a special case, a special case of this case, which is already special, a special case, because now if we take the limit as beta, which goes to infinity of this model, okay, the effect of taking beta, which goes to infinity, is that the model becomes fully packed, in the sense that if we take the limit as beta, which goes to infinity, then the local time of each vertex is precisely 1. And we obtain in this case the so-called double dimer model. Okay, this is an example of a configuration of the double dimer model, which equivalently can be obtained from the original definition just by choosing the weight function, which is the indicator that the local time is precisely 1. And so the model is referred to as double dimer model in the special case where n equals 2. Okay, let me explain what is the double dimer model and explain this connection more precisely. So what is a dimer configuration? So a dimer configuration is a subgraph of the box. We should think of the box as a graph with edges connecting nearest neighbors. It is a subgraph such that each vertex has degree precisely 1. You see in the figure 2 examples of dimer configurations. And now what you can do is to draw 2 independent dimer configurations at random uniformly on the set of dimer configurations. And you can draw 2 dimer configurations independently at random and superimpose them. And what you obtain is a random loop model, as the one that you see in the figure. Well, it's a random loop configuration. Okay, there is of course a difference with respect to the model which we presented, because in our definition, the loops have a label and get a start, and also have a starting point, so they are rooted, while the loops that you see here do not have a starting point and are unlabeled. But then the labels and the roots can be averaged out thanks to these factors which appear in the denominator of our measure. And so the 2 models are precisely equivalent when n equal to. Indeed, in our measure, we have a factor n to the n half to the number of loops. But when n equals 2, this factor is 1. And in addition, each loop has 2 orientations. While in this model, one should also observe that each loop does not have two orientation, but may appear with two different alternations of blue and red dimers. For example, in this loop, we have red, blue, but this might also appear with blue, red. So these are precisely the same. This is true for loops which have length at least 4. And okay, the dimer model, so we have only one dimer configuration, is well understood starting from the work of Castellane, which invented a method for computing very efficiently the number of dimer configurations on planar graphs. And thanks to this method, which has been derived by Castellane, it was possible to have a very deep understanding of such random loop model of namely the double dimer model in 2 dimensions. For example, some conformal invariance properties of the scaling limit have been proved, and the expectation of several observables in 2 dimensions have been proved. For example, the number of loops surrounding 2 distant vertices. And also some conjectures to Schramm-Liouville evolution have been formulated. But the behavior of this class of models is entirely open in higher dimensions. And this is essentially what we want to do, is then to understand the behavior of this model in higher dimensions, in which case these tools are not viable. Okay, another relevant case is the Loophole model, which has been introduced essentially as an approximation of the spin-one model. And it is also interesting because it is, in a certain sense, a generalization of the easy model, and also it exhibits conformal invariance properties on planar graphs. And there are several different versions of this model. I just give the definition, which is the easiest to give. So in the Loophole model, sigma is the set of spanning subgraphs of a certain graph, which in this case is considered to be the box with edges connecting nearest neighbor vertices, such that each vertex is degree 0 or 2. And which means that if you take an element in sigma, each connected component of the graph omega is either an isolated vertex or a loop, because of the constraint that each vertex is degree 0 or 2. And we define a probability measure on sigma, which gives the weights as follows. So we have 1 divided by a normalization factor, which makes P a probability measure. Then we have beta to the total loop length. Well, it's just the total, the number of edges of the subgraph omega, which is precisely also a factor that we have in our measure. And then we have n to the total number of loops in omega. So as before, one should observe that, okay, here the loops are have no starting point and do not have a label, while in our definition, the loops do have these features, but the number of starting points and the label can be averaged out. Also, the loops have no orientation, but there is a factor n to the total number of loops. While in our model, the loops do have an orientation, but the factor is n½ to the total number of loops. So the situation is precisely equivalent because each loop has multiplicity n, in a sense, in both cases. And in this, there have been several results about this model on the planar case, and more precisely on the hexagonal lattice, in which case the loops look like the red connected components, which you see in the figure. On the hexagonal lattice, part of the phase diagram has been understood. In particular, one expects that there is a critical vertical line above the case n equal 2, such that if we are on the right on this vertical line, we see this is beta. If we are on the right of this vertical line, we see no phase transition with respect to the variation of the parameter beta. So the loops are always short for any value of beta. While if you are on the left of this vertical line, then we do see a phase transition. So if beta is small, the loops are short, and if beta is large, okay, there exists some macroscopic loops. Okay, only some part of the phase diagram has been proved. So the blue lines correspond to the lines where something has been proved, something about existence of long loops has been proved. And as an example, let me state a theorem which is known for this model, and it will be interesting to compare it to what we prove in higher dimensions. So if n is between 1 and 2 and beta satisfies, beta is critical, satisfies then the identity which I wrote, then some macroscopic loops occur, and the statement is as follows. So essentially, you have to consider the hexagonal lattice where, so you should imagine that the graph is made of hexagons, and you have to make a very special choice of the set. So you have to consider on the hexagonal lattice a box of radius 2k minus a box of radius k. So this will be an annulus, which means that the subgraph, so the loops do not live in this hole, in this smaller box. This is just a hole. And the random loops just live in this annulus. And the result is that with uniformly positive probability, uniformly with respect to the size of this annulus, there exists a loop which surrounds the hole. So there exists a macroscopic loop in the annulus, as the red one that you see in the picture. And as we will see in higher dimension, we have instead a much stronger notion of occurrence of macroscopic loops. And the tools which are used to here are very specific of the planar case. So there are some complex analytic techniques, and also a planar duality with a spin system is used, and some FKG inequalities which use precisely this planar duality. And the question is, what can we say about this class of models, again, in higher dimensions? Okay, so another interesting case
Lorenzo,
is the case.
That's a question.
Yes.
I think this theorem was about the critical point, right? So that's why this P is bounded from below and above.
Yes, exactly.
It's not only about the existence of macroscopic loops. So I assume that if beta is larger than this critical value, then this probability will be 1 in the infinite volume limit.
Yes, exactly. So, so indeed, something has been proved in the blue part of the phase diagram, even above I just wanted to make an example of a theorem which was proved about long loops. But as we will see, in any case, the notion that we have about macroscopic loops in higher dimension is much stronger than what we have here. I will make this comment later, not only for the fact that this probability is bounded away from 1 or not. Okay, here the irrelevant fact is that this probability is uniformly positive. And yes, but as you said, if we are above the line, there should be even a stronger notion of macroscopic loops. This probability will be 1. In the limit. So, okay, now the interacting Bose gas. So I decided not to define the full framework for time reason in detail, but I'm happy to do it in the discussion session. So, okay, so the model that I'm considering is related to the interacting Bose gas, which is a model for a gas of interacting bosons. And so I will not formulate the framework, which is the analytic framework of, okay, we will not define the model precisely, which will need to require the analytic framework of quantum mechanics. So an important open question for this model is Bose-Einstein condensation, which is a phenomenon predicted by Einstein, corresponding to the fact that as the inverse temperature in this model is large enough, one expects the presence, well, the occurrence of Bose-Einstein condensation, namely the fact that a macroscopic number of bosons occupy the lowest energy state, and for the Nobel Prize for Physics was given in 2001 for the experimental observation of Bose-Einstein condensation, which occurred in 1995. So I can define the question more precisely. Well, I can define the question in this framework in the discussion session. I just want to mention that it is possible to reformulate the question of Bose-Einstein condensation as a question which involves a gas of random loops. And this formulation is rigorously formalized by Ginibre and uses the Feynman-Katz formula. And this formulation involves a gas of continuous time, simple random walk trajectories on ZD. And according to Feynman criterion for Bose-Einstein condensation, Bose-Einstein condensation in the random walk loop soup can be formulated as the fact that as the inverse temperature in this model is large enough, then we suddenly see macroscopic loops in the system, and this is expected to occur in dimension at least 3. And there are other criteria for Bose-Einstein condensation, for example, the more established criterion for Onzager and Penrose. The point that I want to make is that in the probability community, there are many works about occurrence of macroscopic loops in dimension d larger or equal than 3, but in all these models, there is no genuine interaction between the loops, because the loops interact in this model depending on their mutual distance, and also long-range interactions are present in the model. And so what we want to do is to generalize the definition of the random walk loop soup, which I gave before, introducing also long-range interactions. And you want to see whether our technique is able to handle long-range interactions, even though the model that we consider is not precisely the random walk representation of the interacting Bose gas, but it is closely related to. And this is why I'm now redefining the setting, introducing even long-range interactions, and then I will state a very general result about occurrence of macroscopic loops. So in dimension at least 3. Okay, so I'm just recalling the setting that I defined at the beginning of my talk. So G is now going to be always a torus with side length L. And the model again depends on a weight function, U. And V is a potential, so it is a function on ZD, defined on ZD, which assigns to every vertex a real value. And we introduce the function VL, which is essentially the natural way to define a potential in the torus when you have a function which is given in ZD, and just want to define another function which is related to the function V, and it's called VL, in such a way that this new function is invariant under translation, under torus translation. And so V is a general function, and VL is defined depending from starting from B, as you see. And each step of the loop touching X will interact with each step to the loop touching Y according to the function VLXY. Now the definition is then as follows. So the definition of the model, which extends the definition that I gave at the beginning of my talk, is that so the white part is precisely what I wrote before. We have 1 divided by the number of loop factorials. Then we have this factor beta to the length of the loop divided by the length of the loop. Then we have weight function n½ to the number of loops. And in addition, we also have a long range interaction, e to the minus v omega, which is as follows. So, so what's going to happen is that each step of each loop, for example, this step colored now by red, interact with each step of each other loop, and of the same loop also, according to this function, where you just take sum over I and j's, and then you get two loops Li and Lj, and then given two such loops Li and Lj, you sum over all possible pair of steps of these loops and give a weight which depends on the mutual distance between these loops. And if the weight, when V is positive, then this means that we have repulsive interactions, while when V is negative, this means that we have attractive interactions. And okay, we are now ready to state the main theorem about occurrence of macroscopic loops. So if V is, okay, V must fulfill certain assumptions. So it must be tempered. So tempered means, okay, we have a summability assumption. And secondly, we have a second assumption, which can be explained as follows. So we have the sum of two terms, first term and second term. The second term is non-local. It involves non-local interactions and can only be negative. Okay, clearly this condition is fulfilled if the potential is zero. And it is also fulfilled if the first term prevails on the second term. And what does it mean? It means that the non-local total attractive interactions, which are represented by the second term, are weaker than the local repulsive interactions, which are represented by the first term. So the first term must prevail on the second term. And this condition is necessary because if it was not fulfilled, then a collapse transition might occur in this model. So it would be possible that because of two strong attractive interactions, all the loop will collapse, and we will have a region in space with infinite local time. So the potential must be tempered, and if the potential is tempered, then you don't need. If the potential is tempered, and in particular V bar is positive, namely we have strong repulsive interactions given by V, then we don't need the strong condition on the weight function that I gave before. Then in this case, also just the weight function 1 will be good. So because now in the measure we have two terms which somehow establish how the loops interact with each other. So if we have a potential which is non-zero and which is tempered, then you can just ignore the weight function and choose it to be equal to 1. But if the potential is 0, then is 1. So if the potential is 0, then you need a strongly decaying weight function for the well-definiteness of the measure. Okay, so the tempered condition is quite natural. Then we have a further condition which is less natural, which is required by our proof technique. So we need the potential to be separable. What does it mean separable? It means that okay, so I'm actually not giving the definition. I'm just giving two examples of separable potential. And so this condition is to do with the fact that the measure must be reflection positive. And these two examples are such that we have a local repulsive interaction in both cases, and then an attractive interaction which decays exponentially or polynomially with the distance, which is a quite natural physical interaction. And we need to take the L1 norm. So this is also because of our proof technique. And okay, we're now ready to state the general result about occurrence of macroscopic loops, and then we will discuss some implications. So to state the result, I just need to define the loop crossing a certain vertex. So gamma x, I just choose it to be like, define it as the loop, the smallest, or not the smallest, the loop which has the first loop visiting the label x, in the sense that omega is a northern as a label, an ordered sequence of loops, and gamma x is the loop visiting x, which gets the smallest label. So ix is the infimum among all I of the smallest label of a loop visiting x, and gamma x is just defined as this loop if there is a loop visiting x, or the empty set otherwise. Okay, so let us move to the statement of the main theorem, which is a joint work with my PhD student Alexandra Quitman. So, okay, the theorem holds in dimension d at least 3, and the value n that you see in the definition of the measure, which corresponds to the number of components of the spin system, is such that n must be at least 2. This also somehow, and also must be an integer, while the definition of the random walk loop soup does not require n to be necessarily an integer. So if you take d to be at least 3 and n to be at least 2, then there exists an integer r, large enough but finite, which is going to be the range of the weight function, such that uniformly, so in the choice of the potential, v, which must be tempered and separable, and also for any weight function, which must be good, because the measure must be well defined, and also the only assumption that we need is that it needs to have a range at least r. It can have finite range, but we need a lower, but it must allow sufficiently many visits at the vertices, which is a natural condition. Okay, so if so for in any dimension d at least 3, and for any integer which is at least 2, then well, essentially for any choice of the potential which is temperable and separable, and for any choice of the weight function which is good and allows sufficiently many visits at the vertices, we do see a phase transition in this model, corresponding to the occurrence, to the fact that there exists a critical finite value of beta, such that if beta is greater than this critical value, then two facts hold at the same time. The first is telling us that the expected length of the loop visiting any vertex x is proportional to the volume of the system. And the second fact is that if you take fix any two vertices in the torus, which can be taken very far from each other, so proportional to the diameter of the box, then with uniformly positive probability, we see a loop which visits these 2 points. So namely, there exists two constants such that uniformly in the volume and in the choice of the 2 distant points with uniformly positive probability, we see a loop which is precisely crossing these 2 points. So this is a stronger notion of occurrence of macroscopic loops than what you have seen in 2 dimensions, because the statement is not that there exists some macroscopic loop in the box. The statement is that just fix 2 vertices, and then you will find one loop which is visiting precisely with uniformly positive probability that 2 vertices. And the picture should then be that we have some macroscopic loops. Okay, this also follows from numerical simulations, which are space filling, which visits all the regions of the box. And okay, let's just discuss some implication, also making again connection to spin systems. So, okay, one first remark, okay, this extends a result of Benassi and Ulci, who studied essentially a related version of this random walk loop soup in the special case where the weight function is chosen in such a way that the model corresponds to the spin on model with n equal 2. The result is that, okay, they generalize this, they consider a version of this random walk loop soup where the loops might also enter from the boundary and leave again from the boundary. And then they show that with uniformly, whether there is the expected number of loops which enter from the boundary, leave from the boundary, and cross the origin is uniformly positive in the volume of the system. And well, contrary to the work of Benassi and Dulci, so we do not deduce our result of macroscopic loops from the work of Fröhlich, Salmon, and Spencer, which is about namely from the uniform positivity of the two-point function for the spin system, but we just reformulate the technique in the space of random walk trajectories. This is why the result holds in wide generality over the choice of the interaction, which then includes, for example, the model that I stated at the beginning, where we have some hardcore constraints. So it includes these models. And okay, secondly, also so our result so can be reformulated back in the space of spins, and implies that for arbitrary values of n, correlations which are not the classical spin-spin correlations, but correlations of the form Sx1, Sx2 times Sy1, Sy2 are uniformly positive, where Sxi is the ith component of the spin. And I'm not aware of different results which allow to deduce from the result of Fröhlich, Salmon, and Spencer uniform positivity at this type of correlations for arbitrary values of n. And it is not, so our result implies the occurrence of phase transition, because it is not hard to prove that if beta is small, then the expected length of the loop touching any vertex is of order 1. And the probability of having a loop connecting two vertices is exponentially small with the distance between these two vertices. And I want to refer to this situation as the fact that the loops are short. So if this inequality is fulfilled uniformly in the volume and for any x and y, then we say that the loops are short. And okay, and our result complements a previous result from Chase, Priatko, and Stengel, who looked at this class of models when in dimension d at least 2. And in the case where the range of the weight function is finite, so we have an upper bound on the maximal number of loops which are allowed to touch a given vertex. And what they show is that if n is large enough, then uniformly in beta, the loops are short. While our result is complementary, because what we said is that what we prove is that if you take, well, it's complementary in dimension at least 3. So what we prove is that as I wrote, that if you fix d and n, then there exists a range of the weight function large enough such that we do see a phase transition. And more precisely, when the weight function is finite, whereas a finite range, there is always a critical value of n such that if n is larger than this critical value, then we do not see any phase transition as n is larger with respect to beta. And our result implies then that if the dimension is at least 3, then the critical value of n goes to infinity as we take the range of the weight function to infinity. And the behavior of these models as n is larger is extremely interesting in dimension, especially in dimension 2, because there is a very important open conjecture, which is known as Polyakov conjecture, which can be formulated in the space of spins or also in the space of loops. So the conjecture states that if the dimension is 2, then for any good weight function, so you should have u, this critical value is always 2. So as you take as you take any value of n, which is strictly greater than 2, then no phase transition occurs with respect to the variation of the parameter beta. And the conjecture is known as Polyakov conjecture in the special case where we consider the spin-1 model. So in that case, as we observed the weight function at infinite range, and then the conjecture is that if d is 2 and n is strictly greater than 2, then uniformly in beta, okay, if we look at the loop model, loops are short in the sense that I defined before, and that the correlations between spins decay exponentially fast. And okay, so now I can, in the remaining, I think 5 minutes, if I'm not mistaken, I can well, just briefly describe the proof method. I think there is no time to discuss this universal property of such a random walk loop soup. So, okay, the crucial property of the measure that we use is reflection positivity. And with essentially, I'm going to now to define reflection positivity in the space of closed random walk trajectories. So TL is a torus, and R is our reflection plane. So for example, the red plane, which you see in the picture, and theta is a reflection operator, which assigns to each vertex another vertex. For example, this vertex is reflected with respect to the reflection plane and is then mapped to this vertex here. And then this reflection operator naturally identifies two disjoint regions of the torus such that TL plus is mapped to TL minus and TL minus is mapped to TL plus. The two regions are called TL plus and TL minus, and they are colored by blue and red. And theta can be also, the reflection operator, the definition can be extended to the space of configuration. So we can define, so given a configuration omega with its labels, we can extend, well, so we can define reflection with respect to R, just as in the picture. So you just take the whole configuration and reflect with respect to R. This would be the definition of theta omega. So so let us define also the reflection of a function. So f, so the reflected function theta f is then f evaluated at the reflected configuration, theta minus 1 omega. And to state this powerful correlation inequality, we need to define the set A plus, which is the set of functions which well, are label, starting point, and orientation independent. So they are defined on omega, but do not depend on certain feature of the configuration, the orientation, the label of the loop, and the starting point. And in particular, and moreover, they depend, so A plus will be a set of functions which depend only on omega through its restriction to T plus. So they are, they only depend on what does the loops do inside the region TL plus and not on what happens on TL minus. So the inequality is that now take any pair of functions f and g. The well, it is a correlation inequality. The expectation of f times theta g squared is less or equal to the expectation f times theta f times the expectation of t g times theta g. For example, okay, if you take two regions A and B, which are in TL plus, and take two functions f, which is the indicator that a loop crosses A, and g is the indicator that a loop crosses B, then the inequality will be that the probability that we have a loop crossing A and theta B squared is less or equal than the probability of a loop crossing A and theta A times the probability of a loop crossing B and theta B. And this is useful because it allows to make comparison between probability of events, and in many applications it is used iteratively, this type of inequality. So, so I will sketch in 3 minutes then the general proof strategy. So gx, so we work with a function gx, which is a 2-point function, which I do not define precisely, and which is related to the expected number of loops which visit the origin and x. It would be great and is simpler if the method could work directly for this expectation, but we cannot work directly with this expectation. We have to work with some different function which is related to this expectation. And the goal is then to also to make this connection between this function gx and the expectation. And then one defines the Fourier transform of the 2-point function. And by using some simple identities based on the definition of the Fourier transform and the inverse Fourier transform, we have that the C0 sum of this 2-point function is equal to the 2-point function evaluated at 2 points minus the sum over non-zero Fourier modes. And okay, and this is it's a very simple identity, follows from the definition of Fourier transform. And so in the first step, what one does is to lower bound G0. So the goal is to show that this C0 sum is uniformly positive. For that one, lower bounds G1 and just uses the trivial bound that G0 is at least 0, because for many models which belong to our general random walk club soup, G0 is just too small. And so on the first step, we lower bound E1. We also use reflection positivity here to show that G1 is large as the range is large and as beta is large. And then one provides an upper bound for the term which is underlined by red, again using by reflection positivity. And here there are some important differences with the case of the spin system. For example, in this case, we do not have Gaussian domination. So there is for who knows the proof in this framework of spin systems, there is an important step which is called Gaussian domination. So here the Gaussian domination does not hold. There is some weaker version of Gaussian domination. And from the comparison, one deduces the uniform positivity of the C0 sum of the 2-point function. From some general monotonicity property of Gx, site monotonicity property, one deduces that Gx is uniformly positive. This is the fourth step. And the last step is to relate the uniform positivity of this 2-point function to the uniform positivity of the probability of existence of a loop connecting 0 to x. Here also, we use some probabilistic estimates and reflection positivity, and also so the difficulty is also the presence of long-range interactions. And overall, essentially, we work with a reformulation of the random walk loop soup, which I will not have the time to give. So I just wanted to give the overall strategy. So I guess that my time is over, so I will not have time to talk briefly about the conjecture about the universal properties of this random walk loop soup in higher dimensions. So my goal was to explain somehow the fact that there is an interesting conjecture about the fact that in higher dimension, all these very general random walk loop soup are expected to show the same scaling limit if we look at the distribution of the loop length. So I think I can then, and this scaling limit is related to the Poisson distribution. So I can then conclude, and I thank you for your attention.
Thank you very much. Thank you, Lorenzo. This is very nice talk. Are there any questions?
Yes.
Go ahead.
So how hard it will be to prove the existence of Bose-Einstein condensation in the sense of long-range off-diagonal correlation?
Yes, so it is actually not, so in the sense, okay, for this random walk loop soup, which I defined, which is not precisely corresponding to the random loop representation of the random walk of the Bose gas. But it is closely related, but it's not precisely the same. But if I translate somehow the question of Bose-Einstein condensation according to the notion of that you mentioned of Onzagar and Pendrose, then so Bose-Einstein condensation in the framework of this random walk loop soup will correspond to the fact that a ratio of partition functions with the denominator of this partition function in the denominator corresponding to the partition function of the random walk loop soup with all loops being closed, and the partition function in the numerator corresponding to a modified object where we have similar to the spin system, where we have walk connecting 2 points. well, that this ratio is uniformly positive. This will be the reformulation of Bose-Einstein condensation in this framework. I think I have the picture here. So yes, exactly. So it will be a ratio of two partition functions. At the numerator, we have, well, it's basically a modification of the partition function of the model where we have a random walk from X to Y. So, okay, the technique would allow also to provide a result about uniform positivity of this ratio of partition functions, but it will be for the model which I considered, which is not precisely the random loop representation of the Bose gas, because I didn't define it because of some details in the way as the interaction in some details. There are some little details in the definition of the measure, which are such that the model which I define does not precisely correspond to that model. But for the model that I define, the same technique would allow to prove the uniform positivity of the ratio of these two partition functions. Indeed, in a previous paper, I addressed precisely this question, and there essentially I show that under a specific choice of the weight function, in particular, one can also obtain some new results about the dimer model in dimension at least greater than 3, and the goal there is precisely to prove uniform positivity of this ratio of partition functions.
Okay, yeah, thank you.
Any more questions? So please unmute yourself.
Perhaps one question. So you have a regime of long loops, a regime of small loops, but you also consider attractive interactions. So there could be also a regime where you get loops which are aggregating. So like when the strong attractions, I mean, even if you have hardcore repulsions, but the strong attractions would kind of make a ball of a loop. Is this something that you can see that the
yes, no, so essentially this is, I think this behavior is excluded by the assumption that we have on the potential. So because, so we have these two assumptions, which, okay, so first of all, if we consider, exactly, okay, so let's consider, for example, long-range interactions. Okay, so the potential can be positive or negative. Positive means repulsive interactions, and negative means attractive interactions. And our technique only works if this condition is fulfilled. And the condition B means that, so if you see the second term is just the sum over all vertices, then we have, it catches only the contribution of the attractive interactions. And in the first term, instead, we have well, the local interactions, and if the sum of the two terms is strictly positive, this means that the first term somehow prevails on the second term. The first term must necessarily be positive and must prevail on the second term, which might be negative.
But I'm not sure it's correct, because you could have a V0 to be infinite, so that the loop is kind of self-avoiding, but at the same time very strong, let's say, nearest neighbor attractions. So
V0, okay, in this case is it cannot be, so just a positive real value. I don't know if it can be.
But it could be arbitrarily large, and still you may have this regime where you get this aggregation.
The tempered condition, so okay, this when this shouldn't happen, because I think this condition just prevents this from happening. Okay, otherwise it will not be possible to have macroscopic loops in this case. So this will be a contradiction with the result that we prove, because this will be the situation in which okay, all the loops are condensated, are okay in one small region, and Yes, and then it's not possible for the loops to be macroscopic. So there would be.
Yeah, indeed, there should be a contradiction with your results, but I just
Yes.
want to.
So I think this condition prevents this
Mhm.
from happening because exactly because the repulsive interactions are in any case stronger than the attractive interactions.
Okay, yeah, thanks. I need to think about it.
But I think you may have a percolation of small loops, right? So actually you had that picture. So
yes,
if beta
exactly.
is very, very small, then you have sort of gas of small loops. That's very boring, but probably you could have an intermediate phase with small loops showing percolation cluster. Yeah, this one.
Yes, exactly. So this, okay, yes. So essentially, there should be such a phase transition as you mentioned, as we define the weight function, which in such a way that, so essentially, if the weight function allows sufficiently many visits at the vertices, and beta is chosen to be large enough, then there will probably first be a transition into such an intermediate regime with small loops which percolate. And then if beta is taken to be even larger, then there will be a phase transition, or a second phase transition into a regime with macroscopic loops. But essentially, proving the occurrence of the first regime is simpler than proving the occurrence of the second regime. So the occurrence of macroscopic loops implies the occurrence of macroscopic connected components,
right?
But not the other way around. So okay, we didn't care of proving the occurrence of this intermediate regime, but I think it should be possible because it's not hard to prove that. Using also reflection positivity, that if the weight function allows sufficiently many visits and the inverse temperature is large enough, then the probability of having an edge crossed by a loop goes to 1. Well, in the limit. So essentially, with probability going to 1, the crossing probability, the probability of having an edge being open is close to 1. But indeed, it is an interesting observation that there is somehow an intermediate regime for certain choices of the weight function.
Thank you.
Okay, any more questions, comments? Jan?
You mentioned parafermions. What are they and how are they used?
Yes, okay, this is, this involves some of the work of Dominique Copin and Coulter, Spellet, and it is, which I mentioned here. So it is an analytic technique which is which works only if we consider the hexagonal lattice, and I cannot find this here. Only if we consider the hexagonal lattice. In particular, we need to have that the degree of the graph is precisely 3, and it is not the only tool which is necessary. There are several other tools which are necessary, and I think I will prefer to refer to the paper because it is about different work. My goal here was to compare the result of the occurrence of macroscopic loops in 2 dimension, which uses these analytic techniques which are viable in the specific case with the case of higher dimensions.
Thank you.
Okay, more questions? Comments? Well, we have a couple of minutes left, so maybe Lorenzo, you could comment on the last conjecture that you had to go through very quickly.
Yes, okay, this is a very interesting conjecture, and it involves all the random loop models which I mentioned, and in dimension at least 3. So let us go to the part talk. Exactly. So the idea is that in all these models, even in the regime where we have macroscopic loops, we should always have a density of very small loops. And not only that, but also the idea is that we have a very specific distribution for the law of the loops, of the length of the loops. So, okay, take any random walk loop soup defined before and let L1, L2, L omega be the length of the loops ordered in decreasing order. So L1 is the length of the longest loop. L2 is the length of the second longest loop, and so on. And okay, now V is the total loop length, and Li tilde is the length of the ith longest loop divided by the total loop length. Okay, it is of course a number between 0 and 1. And now, okay, let us partition the set 0, 1 in the following way. So, okay, so in the first segment corresponds to L1 tilde. So the second segment corresponds to L2 tilde, and by definition should be a bit shorter than the first segment. Then the third segment corresponds to L3 tilde, and so on. So if we proceed as follows in this way, so what we would observe in the regime where macroscopic loops occur is that in the limit, as n which goes to infinity, we shall have an accumulation point at a point which we call m, which will only depend on the dimension, on the weight function, and on beta, and which is positive is u if the range, well, which is positive, okay, if the conditions of the theorem which is stated are fulfilled. And if we continue, then we then, on the right of this point m, we should have the contribution of the loops which are microscopic, so which are small. So on the right of this accumulation point m, we see loops whose length does not grow with the size of the system, but stays of order 1. While on the right, we see the contribution of loops whose length grows with the size of the system as the volume, and this is the contribution of macroscopic loops. Okay, and the conjecture is that the set, well, we get a random partition of the set 0m, and that this random partition has a very specific distribution, which is the same for all the models which I define, and which will only depend on the value n, which it appears in the definition. And more precisely, the conjecture is that the partition of 0m is distributed according to the Poisson Dirichlet distribution with parameter n-half, where the Poisson Dirichlet distribution is a distribution of a random partition of the set 0, 1. In particular, this was proved for the free Bose gas without interaction, namely for the model of the Bose gas without interaction. Okay, what is the Poisson Dirichlet distribution? Let's say, for example, with parameter 1, I just define it with parameter 1. It is defined as follows. So distribution of the partition of 0, 1 is defined, so it is random distribution of the partition of 0, 1 such that defined as follows. So let y1, y2, and so on be sequence of IID random variables with uniform distribution in 0, 1. And in the first step, we construct the sequence y1, 1 minus y1, y2, 1 minus y1, 1 minus y2, y3, and so on, which is a sequence which clearly converges to, where sum converges to 1. And then we rearrange the sequence in decreasing order. So, and after that, we obtain a partition, well, which maybe I should do it a bit larger. We obtain a partition of 0, 1. And the conjecture is that in all the models which I defined before. So if I consider the scaling limit as L which goes to infinity, and I take and I consider the first n element of the partition, and they're scaled by m, then obtain that this first this sequence converges to the Poisson dirichlet distribution with parameter n½ restricted to the first n elements. And in particular, what we learn from this conjecture, we learn, for example, that, well, in percolation, for example, it is an interesting question that whether there is a unique percolation cluster or we have multiple percolation clusters. It is known that in ZD we have a unique macroscopic percolation cluster. Then you can ask here, do we have a unique macroscopic loops or do we have multiple macroscopic loops? Well, from this conjecture implies that we have multiple macroscopic loops. And also, that we always have a density of short loops. And the scaling limit of these models is characterized, not the cases, by the Poisson dirichlet distribution. So similarly to the two-dimensional models, where there is also a universal behavior, which is characterized by Schramm-Lehmann evolution and by the fact that we have conformal invariance properties of the scaling limits. So here, the universal property involves the law of the length of the loops.
Nice.
Excuse me, what is the Poisson-Dirichlet distribution?
Yes, the Poisson-Dirichlet distribution is the resulting partition which follows from this process which I've defined. So yes. I define the Poisson-Dirichlet distribution with parameter 1. It can be defined more generally for parameter n. So just for simplicity, gave the definition of the Poisson-Dirichlet distribution with parameter 1. And it is that, as I said, so take the sequence y1, y2, y3, so which are IID random variables with uniform distribution in 0, 1. And now construct the sequence y1, 1 minus y1, y2, and so on. Okay, this is just a sequence of random variables also. And you can rearrange the sequence in decreasing order. And then after you rearrange the sequence in decreasing order, you construct a partition of the set 0, 1 in the same way as I did before. So the first segment will correspond to the largest number, then the second segment will correspond to the second largest number, the third segment will correspond to the third largest number, and so on. And then you get, as you see, a random partition of the segment 0, 1. And these,
so it depends on an infinite number of parameters, y1, y2, and y3, etc.
So the parameter is, yes, so exactly. So what I define is, for simplicity, it's just the Poisson-Dirichlet distribution with parameter 1. I didn't give the definition of the Poisson-Dirichlet distribution with parameter n, where n can be an arbitrary real number.
The y's are random variables.
Okay.
Yes, the y's are random variables.
There is one parameter and many random variables.
Yes, yes, there is one parameter. Yes, the parameter here, just what I chose is 1, and the sequence is a sequence of random variables. And then it is a distribution of a random partition of the set 0, 1. So these numbers here are, so these points here are some random points which have a certain distribution, which is called Poisson-Dirichlet distribution. And all the random loop models I considered, well, in the scaling limit, according to the procedure which I define, are characterized by this Poisson-Dirichlet distribution. Well, to define the distribution for arbitrary values, you should, instead of taking yi to be uniform, to have uniform distribution in 0, 1, you should consider another distribution, which is the beta distribution with parameter with a certain parameter.
Okay, well, I think we can maybe stop the official part of the talk. So thank you again, Lorenzo. This was very interesting.
Thanks again.